Okay, next talk before the break, no, yes. Ying Tong, and she will be talking about next-gen lookup arguments.
Thank you. So, yeah, lookup arguments are this primitive that have been getting lots of attention in the zk world. And in the recent few months, we've had huge advancements in the efficiency of lookup arguments. So this talk is a high-level overview of the latest techniques in lookup arguments. And this is an outline of the talk. We're going to start with basically our motivation, why we're interested in lookups. So a really sort of motivating factor is the so-called lookup singularity. And this was an idea that Barry Whitehat came up with in 2022. So this idea is pretty much the full outsourcing of all in-circuit operations to lookup tables. So in other words, instead of writing bespoke opcodes, bespoke constraints for each opcode, in the lookup singularity, we would simply pre-compute the inputs and outputs and dump them into a table. And then our whole circuit would just be a series of lookups into these pre-computed tables. Jolt is an example of a zk virtual machine following this design principle. So in Jolt, all instructions are indeed just lookups. And furthermore, they have a memory checking argument for the virtual machine's random access memory. And besides that, they just have a few very simple constraints to check that the lookup and the memory check is being done correctly. And so the benefit of this paradigm is that I think a big benefit is that we have a lot less to audit, and we can really, auditing would just be sort of checking the computation of the tables. And this is a big benefit for anyone who's written a zk circuit. There's really any number of bugs lurking in your circuit. So yeah, I've been sort of thinking about how to classify the different use cases for lookups. And this is my own classifications. You might agree or disagree. So we're probably the most familiar with fixed decomposable lookups. So basically, these are highly structured tables with very well-defined domains. And it's possible to pre-compute them ahead of time. For example, range checks. Literally, your table is just an enumeration of all like 13-bit values, let's say. Bitwise operations, your table is just enumerating all like 2-bit inputs, let's say. And the point here is that these are decomposable in that, for example, when computing an XOR, you can separate the input into smaller chunks, XOR those, and then recompose the output to the same effect. Whereas there's also fixed lookups that are not decomposable, so that they don't have that nice structure. For example, RISC-V instructions, it is really meaningless to take apart the inputs to a RISC-V instruction and then put it back together. That makes no sense. ReLU, rectified linear units, is another example. And SHA-256 in its internals has a bunch of bit rotations that are also tricky to decompose. Now these are fixed lookups. The point here is that you can pre-process all of this. All these tables, you can shift it to the setup stage, and this costs the prover very little. But when we come to dynamic lookups, this is sort of the regime where the lookup table is the same size as the input. So whereas, in let's say all the possible 18-bit values, we only look up 1 or 2, when it comes to dynamic lookups, we are often accessing every value in the table. So for example, this diagram is a little bit old, but so the ZK, one of the ZK EVM designs uses this sort of cross-circuit lookup to check that the memory accesses done by each subcircuit is basically following the rules of memory updates. So yeah, every read and write is used somewhere. In other words, at some point, you need to read the whole table. And that's not true for the fixed lookups. For fixed lookups, I think we never read the whole table, yeah. And then this last quadrant is, I think, the newest one. So it's, so over here I'm using decomposable in a very imprecise way. So if you've read the Lasso paper, they have a formal definition for decomposable. But over here, I just mean that it's a dynamic lookup that is split up across many recursive steps. And this was recently sort of, so this last quadrant was recently elaborated on in a paper called Proofs for Deep Thought. So all the decomposable lookups share this feature that the table is way larger than the input, right? In the case of this, in the recursive setting, at each step, you're only doing very few reads or writes. And at each step, you only want to pay for the reads and writes you're doing. And the fixed lookups also have this feature, that the tables are huge and we only really access very few entries in them. But as we mentioned just now, the dynamic monolithic lookups have equally sized tables and inputs. So over here, I've listed what I think is the state of the art in each of these quadrants. Again, you might agree or disagree, and I'm sure I've left out some things. But yeah, how am I doing on time? Somebody tell me.
I don't know. I was doing that. Expect that you should have 15 more minutes.
Okay.
15.
Okay, if I only have 15 more minutes, I'm gonna skip this section. So this section was sort of a disambiguation of terminology. It was me trying to separate these terms that have come up recently and have sort of sometimes been used interchangeably. And I'll just skip to the punchline, which is, you can interpret this diagram as like how you would complexity classes, kind of. So memory checking is like the most powerful primitive, and multi-set equality is the least powerful. And basically, you see multi-set equality being used as a primitive in lots of lookup arguments. And then index lookups is when you specify not just the inputs, but also their position in the table. So this is really a more like nitpicky, technical kind of disambiguation. We can skip that. So yeah, now that we have sort of motivation why lookups are interesting, let's look into lookup arguments and the recent advancements. So yeah, this is a timeline of lookup arguments. Now, up till 2022, we only had lookup arguments that were O(n) in the size of the table, meaning like even if we're only accessing a few inputs in the table, we will still have to pay for the whole table. And sadly, that was the case up till 2022. But with the introduction of Calc+, we got a lookup argument that was independent of the table size. So yeah, it was OM squared, M being the number of inputs. And once again, how they achieve this is through pre-processing. And then most recently, the proofs for deep thought paper introduced an OM lookup argument, but it's important to note that this OM is for the work of the accumulation prover. So we're in the setting where over many accumulation steps, the prover is reading into the table, like a constant number of times, let's say. And if you're familiar with accumulation schemes, at the end, you still have to pay for like a single computation. But while we're just considering the accumulation prover, this paper gives us OM lookup argument. To be more precise, they give OM memory checking argument, but as we saw in this diagram, with the memory checking argument, you can have a lookup argument. Basically, lookup argument is, you can think of it as a read-only memory checking argument. It's a memory that you can only read and you can never write. So here's a timeline, and this table is outdated. It ends at CQ. It was adapted from CQ. And so I think actually why it's difficult to update this table gets to sort of a very core subtlety. So it's difficult in general to benchmark lookups, I think. And the reason being that different lookups are optimized for different use cases. So, for example, to fairly bench the proofs for deep thought, we need to be in the setting of an accumulation scheme. But yeah, when you're in an accumulation scheme, you might make different optimizations than if you were trying to do a larger circuit, like a monolithic circuit. And yeah, it makes also no sense to bench like dynamic versus fixed and decomposable versus monolithic. And basically, depending on what your lookup is optimized for, you're also going to have different implementations, different arithmetizations of the same function. Like, so yeah, even if we fix a certain function like SHA-256, given a different lookup, you're going to have a different strategy. So basically, when I was thinking about how to update this, yeah, even asymptotics, it's hard to say. I have 10 minutes left. But yeah, so I guess with the 10 minutes, what we can do is just a high-level look into a few of these protocols. So basically, I've highlighted those that have implementations in Halo 2 because that's what I'm more familiar with. So I think some people in the audience would be familiar with the Halo 2 lookup. That was sort of the most primitive lookup. And it's very, very intuitive. So if we want to prove that every element of this input appears somewhere in that table, how we could do it is we could sort of permute the input in a table in a very special way. So in particular, we permute the input such that all like values are arranged in adjacent chunks, okay, like contiguous chunks. And then we permute the table such that at the first occurrence of each unique input, it aligns with that same value in the table. And besides these rules, I don't care how you arrange the rest of the values. So what we just said in English here is enforced in polynomial identity form here. And also worth noting that the multi-set equality is used as a primitive to check that you indeed did a full permutation of the input and table. So now, what is the problem with this proto-lookup? Is that it's expensive for the prover. So the prover has to commit to not just the input and the table. And by the way, notice the prover always commits to the full table, even if it's only using like 3 elements in it. And the prover also has to commit to this permuted input and permuted table. So, and commitments in elliptic curve world are expensive. They're full cryptographic operations. So lookup was an improvement on this. And basically, the intuition is that it gets rid of the need to commit to additional helper polynomials. So it expresses the polynomial identity that we saw just now. This is the multi-set equality polynomial identity. It expresses that in a logarithmic derivative form. So you can notice that instead of computing a product, now we're computing sums of fractions. And this is nice because we can check this identity using what's called a sum check protocol. And the sum check protocol is better for the prover because intuitively, it increases the rounds of interaction and decreases the amount of commitments that the prover needs to do. So the prover is engaging in more rounds, but in each round, it's only doing field additions and multiplications, which is cheaper than sending commitments. So the original lookup paper sort of did this. In the end, it still used the normal polynomial identity protocol. And this is what we implemented in Halo 2. And it's actually what Scroll mainnet is using now as well. But I think last year, Lookup GKR improved on this by getting rid of this polynomial identity stuff and just directly proving this rational sum check using the GKR protocol. So yeah, this improved on the vanilla lookup because the prover no longer has to commit to helper polynomials. And, this lookup GKR is sort of more suited to the multilinear polynomials. Whereas vanilla lookup could also be used with univariate polynomials, which is why we had no trouble integrating it with Halo 2. So CQ was inspired by the log derivative identity from lookup, and it was also inspired by the pre-processing techniques from calc and calc plus. So sort of a combination of this that involved a really heavy pre-computation to allow the efficient computation of commitments to polynomials that would otherwise be really expensive to compute. So so once again, CQ is optimizing for monolithic fixed lookups. And so the table sizes you want, it would be like 2 to the 32 or something like that. Huge tables, like that's where CQ really pays off. So we implemented this as well in Halo 2. But we've had trouble benchmarking it because literally the cached quotients are like terabytes in size, and we just didn't know where to put them. Yeah. And lastly, lasso. This is the lookup argument that's used in Jolt. So lasso, so the lookup GKR was actually inspired by a technique in lasso, whereby, so lookup GKR did the sum check directly using the GKR protocol. And in lasso, they did end up with this grand product identity here, which they directly computed using GKR. So this technique inspired lookup GKR. So I'm not sure that I have time to go over the details of lasso, but I guess one interesting thing to note is that internally it uses a memory checking argument. So they call this offline memory checking, and this memory checking argument is read-only in this form, because lasso is a lookup argument, and by getting rid of the write capability of the internal memory checking, they saved some of the cost. So I do want to leave time for the discussion of benchmarks. Like I said just now, it is hard to fairly benchmark protocols that were optimized for different things. yeah, and some protocols just don't work in some contexts, like univariate versus multilinear is a big one. Of course, you can, from a multilinear get a univariate polynomial commitment, but then you pay the cost there, and is it fair to include that in a benchmark, and so on. Some common metrics that we're interested in could be number of commitments, like we discussed. It could be how parallelizable the argument is. It could be how much pre-processing it needs. And also, maybe zero knowledgeness, do we care? This is my last slide that is showing some benchmarks of these different lookups in Halo 2. So you can see like the original Halo 2 lookup is the slowest. This is proving time because you're committing to a whole bunch of stuff. Whereas the fastest over here is lasso and logup GKR, because as we mentioned, both of these use GKR, and this means the prover doesn't have to commit to intermediate values. Fewer commitments, faster prover. And it's important to note that, lasso and logup GKR need the multilinear polynomials. So that's really very different from the univariate vanilla Halo 2 and MV lookup. So I think that's all I had. Thank you.